Hi, thanks for joining me. Today I'm going to be going over problem 1 from week 3 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. This is the problem we have for today, and I've drawn a little sketch of the setup we have over here. So we have 4 lines, L1, L2, L3, and L4, and they're all parallel to one another, and the distance between L1 and L2 is 1, between L2 and L3 is 4, and the distance between L3 and L4 is 1. Now, we have 4 points, AI, so A1, A2, A3, and A4, and AI lies on line Li for each I. And we have the A3 lies left of A4, so the x-coordinate of A3 is less than the x-coordinate of A4. We also have the distance between A3 and A4 is the square root of 26, and these points A3 and A4 are fixed, we can't change them. However, if we look at A1, A2, we have that A1 and A2 are moving, but we keep the distance between them constant at distance root 10. So we have, and we also have A1 lies left of A2, so we have that the x-coordinate of A1 is always going to be less than the x-coordinate of A2, such that their distance, the distance between them is root 10, but we're allowed to move these pairs of points across like so. And the problem we have is we want to find the minimum value of A2, A4 plus A1, A3. So the distance between A2, A4, maybe I should put like bars like that. So the distance between A2, A4, this guy, and the distance between A1, A3. So what is the minimum value of their sum? Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so let's dive into a solution. I've redrawn up the kind of setup we had. However, I've added on a few extra points. I've added on an A1 prime, an A3 prime, and an A4 prime as three additional points to our diagram. So we have A1 here, and I've put A1 prime up here. And the way that we kind of define A1 prime is just simply the point on line L3, which makes this guy here a parallelogram. So A1 prime to A1, up to A2, up to A4, like so. So that guy there's a parallelogram. So A1 is simply the point on L3, which makes A1 prime is simply the point on L3, which makes that guy a parallelogram. Cool. What's A3 prime? Well, that's all the way down here. It's simply the reflection of A3 in line L1. So if I look at the x coordinate of A3, this guy here has the same x coordinate, but its y coordinate is 10 less. Because remember, the distance between L1 and L3 is 1 plus 4, so 5. So if I reflect this in line L1, it's going to have a y coordinate which is 10 less. Cool. So that's A3 prime. And what about A4 prime? This is just A4 shifted down 1. So change the y coordinate by 1. So this is A4, and I brought it down to line L3. So it's perpendicular. So this guy here is a right angle. Cool. So I've just added on 3 additional points, and I've written down a goal here as the first thing we kind of want to prove, and that is that the distance between A2 and A4 plus the distance between A1 and A3, remember that's what we're considering, is always going to be at least the distance between A1 prime and A3 prime. So the distance between this point and this point. And of course, I've got to prove this, and the way I'm going to prove this is by noting that because this guy here is a parallelogram, so if I write down proof, if I call this guy here, well, I'll just write it out. So we've got A1, A3 plus A2, A4, like so. Well, A2, A4 is the length between that, or is just simply that length, but that's the exact same as that length there. So this is equal to A1, A3 plus A1 to A1 prime, like so. But also, we have that A1, A3 is there to there, but just kind of by symmetry, I've taken this point, I've reflected it across here to get A3 prime, so that means that the distance between A1 and A3 prime is the exact same as the distance between A1 and A3. So I can say that this guy here is the same as the distance between A1, A3 prime plus A1 prime. So just changing this A3 to an A3 prime, because the distance between A1 and A3 is the same as the distance between A1 and A3 prime. Cool. So I've got A1, A3 prime plus A1, A1 prime. So I've got A1s in both these expressions, and we want to get an inequality. Hopefully it's clear that the next step is to now use the triangle inequality, because this guy here is going to be bigger than or equal to because I've got, essentially I'm going from A3 prime to A1 and then A1 to A1 prime, so certainly that should take me longer than if I just went directly from A3 prime to A1 prime. So this can be bigger than or equal to A1 prime, A3 prime, which is exactly what we wanted to prove as our goal. So we've proved that A2, A4 plus A1, A3 is bigger than or equal to A1 prime plus A3 prime, just by introducing these points and using the triangle inequality. But now, of course, this is still, not a number, and we want to find a number as a solution, and we've got a bunch of numbers in our problem, so perhaps we can work out what A1 prime, A3 prime is. So it's, remember, this guy here to this guy here, and, well, if we can work out this length, well, then we'll be done, because we already know that this length, A3 to A3 prime, we know that that's 10. So if you can work out this length, then we can use Pythagoras' theorem to work out what this length is. Now, how can we work out this length? Well, we can just use Pythagoras' theorem on the points that we have. So between A3 and A4, we know that the distance there is root 26, and we know that the distance between A4 and A4 prime is 1. So we know that this distance here between A3 and A4, just by Pythagoras' theorem, is going to be the square root of 26 all squared, 26, minus 1 squared, so 25, and then square root of that. So the distance here is going to be 5. Cool, but that doesn't tell us what this distance here is. It tells us what this whole distance here is. So we still need to work out kind of what this remaining distance is. But we can do that because the distance between A1 and A4, the distance between A1 and A4, we can work out again using Pythagoras' theorem. Because we know A1 to A2 is root 10. So that means A1 prime to A4 is also going to be root 10. So if I think about this triangle here and just draw it up here, we've got A1 prime, we've got A4 up here, and A4 prime down here. This distance here is root 10. We know that this side here is 1. So again, Pythagoras' theorem tells us that this guy here is going to be the square root of 10 minus 1 squared, which is square root of 9, which is 3. So this length here is 3. This guy here is 3. It's clearly not drawn to scale because this guy here is 2, but this looks bigger than that guy. But we certainly have that A3 to A1 prime is 2. And so that means that we can work out this guy here just by Pythagoras' theorem. This is going to be equal to the square root of 5 plus 5, which is 10 squared, plus 2 squared, which of course is just square root of 104. Cool. So we've proved that A2, A4 plus A1, A3, the thing we want to find the minimum value of, is always going to be at least square root of 104. Now I claim that this is actually the answer, i.e. there exists a choice of points A1, A2, such that we can get this bound here. But let me clean up the whiteboard first, and then we'll prove that. Okay, so here's a particular choice of A1 and A2, A3 and A4 you could choose. Remember in the question we insisted that A3 and A4 were fixed, but of course this guy here doesn't really depend on the coordinates. Of course, as long as I scale A1, A2 and A3 and A4, if I move them around, translate them by some constant vector, it's not going to change any of the distances. So suppose we had the A3 had coordinates minus 4, 5, and A4 had coordinates 1, 6, like so. So the distance between them certainly is root 26. A3 is to the left of A4. A3 has distance, is kind of, the y coordinate is 1 less, and so on. Then we could define A1 to be minus 3, 0, and then A2 to be 0, 1. And again, we have that this distance here is root 10. A3 is to the left of A2, and of course, A1 has y coordinate 1 bigger than A1. Cool. And we just need to check that we have that the A2, A4 plus A1, A3 is equals square root of 104, and we can just do that very easily. What's A2, A4? This guy, this guy. The way we work it out is just using the Pythagorean theorem. So this is going to be square root of the difference between the x coordinate squared is 1 squared. 6 minus 1 is 5, so plus 5 squared, and that of course is root 26. A1, A3, this guy to this guy, same thing. The difference between the x coordinates is 1, so 1 squared plus 5 squared again. We're going to get square root of 26, and when we add them up, we get 2 root 26. And this, of course, 2 is square root of 4, so this is just the square root of 4 times 26, which is exactly 104, the square root of 104, which is exactly what we wanted. So we can construct A1 and A2 such that the sum of these two distances here is exactly square root of 104, and putting that with the fact that we showed that it must be at least 104, or square root of 104, that solves the problem. Now you might ask, how on earth have I constructed these 2 points here? Well, actually, that's kind of a little exercise for you guys, for the viewers. If you just go back to the analysis we had a second ago, we ask ourselves, well, we showed that this sum here is at least square root of 104. And all you've got to do is analyze that triangle inequality and ask yourself, when does equality hold? And once you ask yourself that, these 2 points will pop out. But as I say, I'll leave that as a little exercise to you, and I do encourage you have a look at that. But this certainly proves that the minimum distance is exactly square root of 104. Anyway, that's all for today's video. Thank you for watching. If you haven't already, please do consider subscribing to the channel and checking out some of the other solution videos and some of my other non-invariance related maths videos as well. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.